Welcome to Module 1 of the course on Advanced Calculus. This module focuses on developing a deep understanding of both differentiation and integration. We will explore how these fundamental concepts are used to analyze and solve real-world problems across engineering, physics, and mathematics. The goal is to empower you with tools that help in modeling change and accumulation in various contexts. Lecture 1: Differentiation using limits and rules. Differentiation is a core principle in calculus. At its heart, it is the mathematical way to describe how a function changes as its input changes. We begin with the idea of a limit. By examining the ratio of changes in a function's output to changes in its input over smaller and smaller intervals, we reach the derivative. While the limit definition gives a conceptual basis, actual calculations rely on established rules. These include the power rule, for expressions with variable exponents. The product rule, for multiplying two functions. The quotient rule, for dividing functions. The chain rule, for composite functions. Together, these rules allow us to differentiate most functions encountered in science and engineering. Lecture 2: Sketching graphs with derivatives. Once a function is differentiated, the resulting derivative can be used to sketch the function's graph and understand its behavior. First, we identify critical points where the derivative is zero or undefined. These points might correspond to peaks, valleys, or inflection points on the graph. Then, we apply the first derivative test to determine where a function is increasing or decreasing. The second derivative test helps us understand concavity, whether a curve bends upward or downward. Additionally, we look at asymptotes. Vertical asymptotes show where a function goes to infinity or becomes undefined. Horizontal or slanted asymptotes describe long-term behavior as inputs grow large. With this knowledge, we can produce an accurate sketch of a function, a skill that's invaluable in disciplines like engineering and economics. Lecture 3: Solving optimization problems. Optimization is all about finding the best solution to a problem, the highest profit, the least cost, or the most efficient path. To solve an optimization problem, we identify the function we want to maximize or minimize. Find its derivative. Locate the critical points. Apply the second derivative test to determine the nature of those points. An example could involve determining the dimensions of a box that has a fixed volume but uses the least material for its surface. These problems are everywhere, from logistics to manufacturing. Lecture 4: Related rates. Related rates problems involve quantities that are changing with respect to time, and they are tied together through an equation. Here's a common scenario: a ladder is sliding down a wall. As the base moves away from the wall, the top descends. Given the rate of movement at one end, we want to find how fast the other end is moving. We approach this by writing an equation that relates the variables, differentiating both sides with respect to time, plugging in known values to solve for the unknown rate. These problems are particularly useful in physics, biology, and real-time data analysis. Lecture 5: Introduction to integration. While differentiation gives us rates of change, integration is concerned with accumulation. If you know how fast something changes, integration lets you find the total change. There are two foundational ideas here. Riemann sums approximate the area under a curve using rectangles. The fundamental theorem of calculus links integration and differentiation, showing that integration undoes differentiation. This theorem allows us to compute exact values for the area under a curve, displacement from a velocity function, and total profit from marginal revenue. Lecture 6: Applications of integration. Integration finds wide application in measuring real-world quantities. Let's explore a few key applications. Arc length: this measures the total length of a curve, essential in engineering and design. Volumes of revolution: when a curve is rotated around an axis, integration tells us the volume of the resulting 3D object. Surface area of revolution: similarly, we can compute the surface area of the object formed by rotating a curve. These techniques are used in designing everything from engine components to architectural structures. Lecture 7: Advanced Techniques of Integration. Sometimes basic integration techniques aren't enough. We use more advanced tools to evaluate complex integrals. Substitution, including inverse substitution, helps simplify complex expressions. Integration by parts is useful for products of functions. Partial fraction decomposition is ideal for rational functions. These techniques allow us to solve integrals that model fluid flow, electromagnetic fields, and economic forecast. Lecture 8: L'Hospitallers rule and indeterminate forms. Certain limits appear undefined at first glance, like 0/0. L'Hospitallers rule helps us evaluate this by comparing the rates of change of the numerator and denominator. This method is particularly helpful in calculus when other techniques fail. It's widely used in analyzing functions that grow rapidly or decline abruptly. Lecture 9: Improper integrals and convergence. Improper integrals deal with infinite limits or unbounded functions. They are important in modeling physical systems that extend indefinitely, like electromagnetic fields or gravitational pull. To evaluate these, we use limits to approach the point of divergence. Determine whether the integral converges to a finite value or diverges to infinity. Understanding convergence helps prevent mathematical errors in simulations and theoretical work. Lecture 10: Infinite series and Taylor expansions. An infinite series is the sum of an unending list of terms. Some series converge to a specific value, others don't. We explore tests to determine convergence and then move to Taylor series, which approximate functions using polynomials. Taylor expansions are incredibly useful for approximating transcendental functions like sine and exponential, solving differential equations, building algorithms in computer simulations. They allow us to work with complex functions using only arithmetic operations and basic algebra. Summary of Module 1. In this first module, we explored differentiation using limits and rules, graph sketching through derivatives, solving optimization and related rates problems, fundamentals and applications of integration, advanced integration techniques, handling indeterminate forms with L'Hospitallers rule, understanding improper integrals, evaluating infinite series and approximating functions with Taylor expansions. These topics form the foundation of analysis and are essential for success in science, engineering, economics, and beyond. In Module 2, we will shift focus to vector calculus, differential equations, linear programming, and topics like eigenvalues, eigenvectors, and matrix operations. Module 2, Vector Calculus, Differential Equations, and Advanced Topics. Lecture 1, Scalars and Vectors. In physics and engineering, quantities are classified as scalars and vectors. Scalars have only magnitude. Examples include temperature, mass, and energy. Vectors have both magnitude and direction. Common examples include velocity, force, and displacement. We represent vectors as directed line segments and can perform operations such as vector addition and subtraction, scalar multiplication, dot product, which produces a scalar, cross product, which results in another vector. Understanding vectors and how they interact lays the groundwork for vector calculus and the analysis of multidimensional systems. Lecture 2, Vector Calculus. Vector calculus extends calculus to functions with vector inputs and outputs. We examine fields where every point in space has a vector or scalar associated with it. 3 primary operations are used in vector calculus. Gradient measures the rate and direction of change in a scalar field. It points in the direction of greatest increase of the function. Divergence applies to vector fields and measures how much the field spreads out from a point. It's key in fluid dynamics and electromagnetism. Curl describes the rotation of a vector field around a point. It tells us how much and in what direction a field curls. Applications of these operations arise in electromagnetism, weather modeling, and fluid flow simulations. Lecture 3: Coordinate Systems. Working in three-dimensional space often requires adapting our methods to the geometry of the problem. Three commonly used coordinate systems are Cartesian coordinates, based on perpendicular x, y, and z axis. Cylindrical coordinates, useful when dealing with problems involving circular symmetry. Spherical coordinates, ideal for problems with spherical symmetry, such as planetary motion. Vector calculus operations like gradient, divergence, and curl change their forms depending on the coordinate system, and choosing the right one simplifies computations. Lecture 4: Eigenvalues and Eigenvectors. Eigenvalues and eigenvectors arise from linear transformations. They describe how vectors are scaled or rotated when transformed. Given a matrix and a non-zero vector, the vector is an eigenvector if multiplying the matrix by it results in a scalar multiple of the same vector. The scalar is called an eigenvalue. These concepts are crucial in structural analysis, vibration systems, principal component analysis in data science, quantum mechanics. Eigenvalues help reduce complex systems into simpler, decoupled systems for analysis. Lecture 5: Matrices and Linear Systems. Matrices are rectangular arrays of numbers that represent linear systems. They are essential for solving equations involving multiple variables. Key concepts include matrix addition and multiplication, determinants, which reveal if a matrix is invertible, inverses, which help solve systems of equations, rank, which tells us about the solvability of systems. By converting systems of equations into matrix form, we can apply powerful numerical methods for large-scale computation. Lecture 6: Differential Equations, First Order. Differential equations describe how quantities change in relation to each other. A first-order differential equation involves the first derivative of an unknown function. Types include separable equations, where variables can be isolated on either side. Linear first-order equations, solved using integrating factors. Exact equations, which can be derived from a potential function. These equations model real-world phenomena like population growth, radioactive decay, and cooling processes. Lecture 7: Second-order differential equations. Second-order differential equations involve the second derivative of a function and often describe systems with acceleration or curvature. A standard form involves homogeneous equations with constant coefficients, characteristic equations to determine solution behavior, solutions using exponential, sine, and cosine functions. Examples include spring mass systems, electrical circuits, oscillatory motion. Second-order equations are also crucial in structural engineering and wave mechanics. Lecture 8: Applications of differential equations. Differential equations are tools for modeling and solving mechanical vibrations, mass spring systems oscillating under various forces. Electrical circuits, RLC circuits obeying second-order dynamics. Population dynamics, logistic and exponential models. Chemical reactions, rate laws and equilibrium modeling. By applying real-world conditions and boundary values, we can predict future behavior of dynamic systems. Lecture 9: Infinite series and convergence. Series are used to represent functions as an infinite sum of terms. But not all series converge to a specific value. Common tests for convergence include the comparison test, the ratio test, the alternating series test, the integral test. Convergent series allow us to approximate functions and values that are otherwise difficult to compute. Lecture 10: Taylor series and function approximation. The Taylor series expands a function into an infinite sum of its derivatives at a single point. It enables us to represent functions like sine, cosine, and exponential with polynomials. Solve differential equations numerically. Analyze physical systems using approximations. Engineers and physicists often use a few terms of the Taylor series for precise, practical approximations in design and analysis. Lecture 11, Linear Programming. Linear programming is a method for optimizing a linear objective function subject to linear constraints. Key steps include identifying decision variables, writing the objective function, establishing constraints, solving using the graphical method or the simplex algorithm. Applications include resource allocation, production scheduling, cost minimization. In operational research and management science, linear programming is a powerful decision-making tool. Lecture 12, Calculus in Physical and Engineering Context. Advanced calculus isn't just abstract mathematics. It's the language of science and engineering. Examples include calculating electrical fields using vector calculus, modeling chemical concentrations with differential equations, determining fluid pressure via integration of stress over a surface, finding optimal designs using Taylor series and derivatives. This integration of theory and application ensures that calculus remains a central pillar of analytical thinking. Summary of Module 2. In this second module, we explored scalars, vectors, and operations involving them, gradient, divergence, and curl in vector calculus, coordinate system transformations, matrix algebra and eigenvalues, first and second order differential equations, infinite series and function approximations. Applications of calculus in science and engineering. Basics of linear programming for optimization. By combining these tools, we can model, solve, and optimize real-world problems ranging from motion and electricity to economics and ecology. Closing remarks. Congratulations! You've completed the Advanced Calculus lecture series. Throughout the 2 modules, you've gained skills in differentiation and integration, function analysis and optimization, vector and matrix operations, solving differential equations, series approximation, multivariable and vector calculus, linear programming. These concepts form the mathematical foundation for advanced engineering, physical sciences, data analytics, and beyond. Keep practicing problems, visualizing concepts, and connecting mathematics to the world around you.